In the quiet, icy depths of space, a staggering 13 billion light-years away, something seemingly impossible is watching us. The James Webb Space Telescope has peered further into the cosmic unknown than any tool before it, discovering things that defy every known law of physics. Unexpectedly, old galaxies, black holes older than we can fathom, and rogue planetary signals cutting through space. If you're someone who's fascinated by the universe's deepest mysteries, hang tight, because what I'm about to share might just blow your mind. Something's seriously off with the universe itself. Scientists thought they had a good grip on how fast the cosmos was expanding. Thanks to the Hubble Space Telescope and their trusty math models, it all seemed to fit like pieces of a cosmic puzzle. But once the James Webb Telescope took a deeper look, everything unraveled. It's like the universe is expanding at two different speeds, depending on where we measure it. Imagine blowing up a balloon where the top stretches way faster than the bottom. Sounds crazy, right? It's not supposed to happen according to the laws of physics, but Webb confirmed a troubling fear. When astronomers measured the expansion rate using special stars called Cepheid variables, they got one answer. But when they calculated it using the cosmic microwave background radiation, they ended up with a totally different number. And we're not just talking about a tiny difference, it's huge. This suggests that our understanding of reality might be way off. Scientists have dubbed this problem the Hubble tension, but that doesn't quite capture how alarming it really is. This isn't just about some measurement mistake or faulty calibration. After researchers checked over 1,000 Cepheid stars across 5 galaxies spread out over 130 million light-years, the contradiction still stood firm. What does it mean? Either our understanding of the universe's mechanics is flawed, or there's some unknown force pulling at the seams of reality. Dark energy, that mysterious thing that drives cosmic expansion, might be acting in ways we never imagined. Different regions of space could be expanding at different rates, creating cosmic rifts that mess with everything we know about space-time. Adam Rees, the lead researcher studying this problem, bluntly stated that after ruling out measurement errors, what remains is the compelling chance that we've fundamentally misunderstood the universe. Using the word exciting feels off when you think about what this could mean. If our basic understanding of cosmic expansion is off, it means our estimates about the universe's age, size, and destiny are all up for debate. Webb's incredible precision has erased any doubts about these measurements. Both it and Hubble are showing the same mind-boggling contradiction. The universe is expanding in a way that breaks the laws of physics as we know them. Just this discovery would be enough to rethink our cosmology textbooks. But Webb kept going. As the telescope dug further into space, it started finding objects and phenomena that shouldn't exist and defy explanation, suggesting that our reality might be even stranger and maybe more perilous than we've ever imagined. This expansion crisis was just the beginning of a string of discoveries, making scientists reconsider everything they know about the cosmos. But what Webb found next makes the expansion issue seem straightforward by comparison. There's not one, but 6 impossible cosmic monsters out there in the ancient universe, rewriting the rules of how galaxies evolve. When James Webb aimed its infrared gaze at what seemed to be an empty space near the Big Dipper, scientists thought they'd spot some newborn galaxies. just starting out in their first billion years. Instead, they stumbled upon 6 huge, mature star systems that seemed way too big for their age. These space behemoths are nearly as packed with stars as our Milky Way, even though they formed when the universe was just 3% of its current age. It's like trying to grow a full-sized oak tree in a mere 3 months. That's pretty much what these galaxies manage to do on a cosmic level. Star-making is usually a slow process, with gravity needing millions of years to gather enough gas and dust to kick off nuclear fusion. Yet these 6 galaxies somehow fast-tracked their way into giant status, while the universe was still in its cosmic crib. This discovery was quite accidental. Astrophysicist Erica Nelson was peering at small sections of Webb's deep space images when she noticed some blurry red dots that seemed way too bright. In astronomy, red light usually signals old light that's been stretched by the universe's expansion as it traveled to Earth. But these objects were both ancient and incredibly bright, a mix that left scientists scratching their heads. Each of these colossal galaxies has between 10 billion and 100 billion stars. To grow so massive so quickly, they must have churned out hundreds of new stars annually for hundreds of millions of years. Compared to our Milky Way, which produces only about 2 new stars a year, these ancient systems were like stellar factories breaking every rule in the book. The team has nicknamed these objects universe breakers because they challenge everything we know about cosmic formation. According to all simulations and models, early universe matter should have come together slowly, merging into larger structures over billions of years. But these 6 galaxies flip that timeline upside down. They propose that the early universe was both organized and complex in ways cosmologists didn't think possible. Either there is an unknown mechanism for rapid galaxy formation, or our basic assumptions about cosmic events are fundamentally flawed. This discovery prompts alarming questions about dark matter's role in early universe development. If galaxies could balloon to such sizes so quickly, it suggests dark matter was gathering and pulling in ordinary matter at speeds far beyond current theories. The unseen structure shaping our universe might be more chaotic and unpredictable than we've imagined. Joel Leja, an astronomer working on these objects, put it best. Looking into the early universe led us to something so unexpected it shakes the very foundation of science. But we'll need more observations using Webb's spectrograph to confirm if these are actual galaxies. What those further studies revealed was even more shocking than expected. A massive entity with the heft of 50 million suns roams through space completely isolated, rewriting the history of the cosmos. In the depths of the early universe, James Webb found an anomaly that defies every existing black hole formation theory. QSO-1 is a supermassive black hole, strikingly without the typical galaxy as a companion. It's essentially an isolated giant, drifting without the usual crowd of billions of stars that typically accompany such massive entities. Most supermassive black holes sit at the centers of galaxies, acting like cosmic anchors, surrounded by swirling disks of stars, gas, and dust. They usually team up with their galactic homes, evolving together as gravity and star formation play out in a cosmic ballet lasting billions of years. But QSO-1 doesn't follow any of those rules. This celestial drifter holds the mass of roughly 50 million suns within an area smaller than our solar system. Imagine Earth as a marble. Even then, QSO-1 would remain invisible, yet it would pack in more mass than hundreds of billions of regular stars. What truly boggles the mind is the timing of this discovery. QSO-1 existed when the universe was just a youngster, around 600 million years after the Big Bang. Normally, black holes form after massive stars die, which means you'd have to wait for the first stars to appear, go through their life cycles, and then spectacularly blow up in supernovas. That usually should take way more than 600 million years. Roberto Maiolino, a Cambridge astrophysicist who identified QSO-1, described the find as completely out of the ordinary. It messes with every theory scientists have come up with for how supermassive black holes came into being in the early universe. 3 explanations are being tossed around to make sense of how QSO-1 exists, and each one is more unsettling than the last. The first theory says some black holes form directly from the collapse of giant gas clouds, skipping over any star phase altogether. The second theory suggests that intermediate mass black holes somehow ballooned incredibly fast by guzzling up matter more quickly than physics would normally allow. The third idea takes the cake for being most unsettling. It posits that QSO-1 might be a primordial black hole, formed in the very first moments of the universe during wild fluctuations just after the Big Bang. If that's true, it means QSO-1 has been hiding in the cosmic shadows since the beginning, hanging around for 13 billion years, waiting for stars and galaxies to show up and shine its way. QSO-1 is just one of hundreds like it that the Webb telescope has spotted. These small red blips are scattered across the early universe, each one potentially a cosmic beast that defies understanding. They're bright with the light of matter getting ripped apart and heated to extremes as it spirals into their gravitational traps. The presence of these naked black holes hints that the early universe was a lot more chaotic and violent than scientists once thought. Instead of cosmic structures forming gradually and systematically, we might be seeing evidence of ancient disasters that might have created big black holes before any stars ever existed. If QSO-1 really is a primordial black hole, it could mean something way more ancient and otherworldly than any galaxy or star. However, QSO-1 wasn't the only baffling black hole that Webb found hiding in the cosmic depths. Black holes older than the first stars are lighting up the universe, and they might have been around since the dawn of creation. It's long been believed that supermassive black holes appeared after the first massive stars died dramatic deaths. This process is thought to take hundreds of millions of years, with gravity gradually pulling together enough stuff to spark nuclear fusion. Stars would live bright but brief lives, then go out in supernovas, leaving behind stellar remnants. But James Webb has uncovered signs of supermassive black holes existing when the universe was a mere 400 million years old, far too early for the usual formation timelines. Andrea Ferrara and his team from the Superior Normal School in Pisa, Italy, proposed an out-there idea to solve this cosmic mystery. What if black holes, instead of stars, were the first major light sources in the universe? Maybe these primordial black holes were formed amid the chaos right after the Big Bang, lurking in the shadows when the universe was still very young. These hypothetical primordial black holes would have emerged through an entirely different way than the star-born black holes we're familiar with. Rather than stars collapsing, these were born from intense density fluctuations in the early cosmic stew, happening just under 5 seconds post-Big Bang. Imagine the universe in its early days as a chaotic pot of energy and matter, with some spots getting so densely packed they become black holes straight away, skipping the star phase entirely. The data from Webb backs up this wild idea. Many luminous objects from the universe's early days seem more like tiny points rather than spread out, hinting they're powered by compact entities instead of massive star groups. When gas approaches a black hole, it heats up to crazy hot levels and shines brightly. From afar, this superheated gas might look nearly identical to starlight. If this hypothesis stands, it would mean that these ancient black holes gobbled up the first gas clouds, growing bigger and heftier even as they illuminated the universe. These giants would have lurked in the dark for hundreds of millions of years, essentially biding their time for the universe to mature enough to feed them. The ramifications are mind-blowing. Primordial black holes might explain the quick ballooning of supermassive black holes early on. They got a jump start of hundreds of millions of years, letting them grow huge well before the first galaxies started forming around them. Yet, this idea brings up even more unsettling questions. If these ancient black holes were widespread back then, they could still be out there now, unseen and undiscovered. Some might even be drifting through our galaxy, ancient witnesses to the universe's explosive start, older than any star we can spot. These prehistoric beasts could change how we grasp cosmic growth. A universe that we thought got its complexity gradually might have actually begun with mighty, massive elements already a part of its framework. Finding these primordial black holes would also shed light on the Big Bang physics, exposing conditions from the universe's earliest seconds that are hard for us to even picture. But Webb's deep looks into these ancient black holes unveiled an even weirder thing, challenging how we understand gravity itself. We have two galaxies crashing into each other like a cosmic train wreck, creating physics phenomena we've never witnessed. When astronomers first spotted what they called the Infinity Galaxy, its shape immediately intrigued them. This cosmic quirk shows two dense red centers, each ringed with a glowing halo, forming a perfect figure 8 that looks just like the infinity symbol. But its peculiar look was just the start of its surprises. The Infinity Galaxy came to be when two sizable disk galaxies collided in a head-on smash that began millions of years ago. While galaxy crashes aren't rare in the universe, this collision made something never seen before. Instead of the usual chaotic merger that destroys both original forms, these two galaxies have held on to their unique identities while also birthing something brand new. The truly astonishing part about this collision is the spot of the supermassive black hole. In typical galaxy mergers, the central black holes of both galaxies eventually spin in toward each other, either merging into one hefty object or tossing one out of the system altogether. The Infinity Galaxy tosses this idea out the window. The supermassive black hole is nestled right between the two galaxy centers, floating in a vast area of glowing hydrogen gas, ripped away from both galaxies during their crash. This arrangement should leave it gravitationally unstable. Instead of just hanging out in the middle, the black hole should be getting pulled toward one nucleus or the other, rather than acting like a cosmic umpire in the middle of a galactic collision. Astronomers Peter Van Dockum and Gabriel Brammer, who made the discovery, think they're seeing what's known as direct collapse black hole formation. Unlike the usual method where black holes form from the death of massive stars, this one may have formed straight from a massive gas cloud collapsing as a result of the galaxy collision. Here's how it works. When these two galaxies smooshed together, they generated huge streams of gas moving between their centers. If the conditions are just right, these gas streams can grow so massive and dense they collapse directly into a black hole without ever becoming stars. First, it's like watching an epic cosmic landslide creating its own gravity well. This process might explain some of the baffling findings the Webb telescope has encountered in the early universe. The telescope has spotted supermassive black holes that are way too hefty for how old they are, expanding much faster than traditional models predict. If black holes can form from collapsing gas clouds right off the bat, they could become supermassive much quicker than we previously assumed. The Infinity Galaxy offers a live-action scene to study this unusual formation method. The black hole seems to be munching on the gas that's flowing between the galactic cores, growing bigger as this cosmic collision carries on. Radio signals show strong energy emissions right from where the black hole should be, proving it's busy devouring matter. But the most unsettling thing about the Infinity Galaxy crash isn't just what's happening now. It's what this discovery hints at regarding the violent events that shaped the early universe. If direct collapse black hole formation was a regular occurrence back in the universe's wild and young days, it means there was a period of intense chaos and destruction that we're just starting to fathom. And all that violence left behind some truly weird things, like stray black holes. Hundreds of lone planets are floating through space in pairs, and they're sending out radio signals that don't make any sense. The James Webb Telescope has identified more than 500 free-floating planets in the Orion Nebula that aren't orbiting any star. These wandering worlds, each about the size of Jupiter, have been kicked out of their original star systems and now roam through the cold void between stars. What really puzzles scientists is that many of them are traveling in pairs, circling each other at distances between 25 and 400 times the space between Earth and the Sun. Scientists refer to these paired drifters as Jupiter mass binary objects, or jumbos, and they confound all existing theories on how planets form. Typically, planets develop in disks of gas and dust around young stars, slowly gathering more material until they reach full size. The gravitational choreography required to create binary planets should be exceedingly rare. Yet, Webb has uncovered a whole bunch of these cosmic duos. The mystery deepened when astronomers turned radio telescopes toward these paired planets and stumbled upon something completely new. Several of these jumbos are sending out radio signals with patterns that have never been observed from planets before. These aren't the standard emissions you'd expect from planets with magnetic fields mingling with charged particles. They're producing radio bursts in gigahertz frequencies, thousands of times higher in pitch than FM radio. On Earth, radio signals at these frequencies originate from technological sources or incredibly energetic cosmic events like pulsars and quasars. Discovering that these signals come from rogue planets implies these worlds are undergoing physical processes not found anywhere in our solar system. The radio waves seem to be tied to the binary nature of these planets. When two massive bodies orbit each other, their complex gravitational interactions can produce strong magnetic fields and electrical currents. Imagine cosmic friction on a scale humans haven't yet seen. These jumbos are like huge electrical generators, fueled by their orbital waltz. Yet, the signals themselves are baffling. Each pair of jumbos gives off a distinct radio pattern, hinting that every binary system has its unique electromagnetic vibe. Some emit constant radio waves, while others send out random bursts with no clear pattern. The possibilities are disturbing. If these isolated planets can produce such powerful radio signals, what else might they be capable of? Their magnetic fields could be massively more intense than anything in our solar system, leading to space weather phenomena that might affect nearby star systems. More unsettling is what the plethora of jumbos suggests about how planetary systems form. If hundreds of these paired worlds exist in one nebula, millions or even billions could be scattered across our galaxy. Each one is a failed solar system, a cosmic mishap where gravitational forces went awry, flinging planets into perpetual darkness. These rogue worlds are cosmic outcasts, forever distant from the warmth and energy of starlight. They drift in endless night, their only warmth from radioactive decay in their cores and the tidal forces from their partner's gravitational pull. As unsettling as these drifting planets are, Webb found worlds that push our understanding of planet creation even further. This next discovery would compel scientists to rethink everything they know about how planets form around young stars. One young star system is throwing basic planet formation rules out the window, crafting worlds from unexpected materials. In the star-forming region called NGC 6357, James Webb spotted a planet-forming disk lacking water but rich in carbon dioxide, right where Earth-like planets are supposed to form. This discovery upends a core belief about how rocky planets form around young stars. Existing models of planet formation assume that the areas around young stars where rocky worlds develop are full of water, ice, and silicate minerals. Water, being one of the most plentiful molecules in the universe, is thought to be crucial for creating habitable worlds. The disk around the star XUE challenges all these assumptions. When Webb turned its near-infrared spectrograph on this system, astronomers expected to find the usual water vapor mixed with other familiar compounds. Instead, they found a disk where carbon dioxide dominates the inner regions, typically where terrestrial planets form. Water is so rare it's almost undetectable, presenting an environment unlike anything scientists have predicted before. This discovery questions everything scientists thought they knew about the chemistry of planetary formation. On Earth, water was key to shaping the planet's geology and atmosphere, and ultimately providing the conditions necessary for life to arise. A developing planet in the XUE-10 system would grow under entirely different chemical circumstances, possibly forming worlds unlike anything in our solar system. Two ideas try to make sense of this strange chemistry, and both have unsettling consequences. The first theory proposes that intense ultraviolet radiation, either from the young star or from massive stars nearby, is sterilizing the disk, breaking apart water and sending hydrogen away while leaving oxygen to bond with carbon. The second, more unsettling theory suggests that the carbon dioxide dominance might come from odd conditions in the dust grains making up the planetary disk. Unlike typical systems where dust grains are coated with water ice, these grains could be covered in carbon dioxide because of the unique environmental conditions around this young star. Either way, the explanation suggests planetary formation can take pathways astronomers never expected. If ultraviolet light can strip water from disks where planets are forming, It indicates many worlds that might support life could lack the crucial chemical ingredients. The galaxy might contain many dry planets rich in carbon dioxide, formed in conditions unfriendly to life-sustaining chemistry. This finding also brings up questions about the variety of planetary systems across the galaxy. If planet formation can result in such varied chemical environments, there could be whole categories of worlds that follow geological and atmospheric rules we've never known. The XUE-10 system is like a natural lab for examining different planetary formation processes. As its planets continue to grow, they'll offer clues about how worlds develop with chemical foundations vastly different from those in our solar system. However, this odd planet-forming chemistry was just one of many atmospheric mysteries Webb revealed. The next target for the telescope would show a world so hostile and alien it challenges our ideas of what a planetary atmosphere is. A world so close to its star that its surface glows like molten metal, yet somehow holds an atmosphere that breaks all planetary science rules. 55 Cancri E orbits its star so near that it completes an entire year in just 18 Earth hours. This hellish planet is tidally locked, meaning one side always faces the star, creating a day side hot enough to melt copper and a night side in endless darkness. Surface temperatures soar beyond 4,000 degrees Fahrenheit, which is hot enough to vaporize almost all known materials. According to planetary physics, this world should have lost its atmosphere eons ago, but James Webb found something unimaginable. This extreme planet not only has an atmosphere, but it's made of substances that shouldn't exist as gases in such intense heat. The atmosphere seems rich in carbon monoxide and carbon dioxide, forming a thick layer around a world that should be as barren as Mercury. This finding was made through precise temperature readings with Webb's mid-infrared tool. When astronomers measured thermal emissions from its day side, they noticed it was cooler than expected. Something was absorbing and moving the star's heat, and only an atmosphere dense enough to carry energy from the scorching day side to the freezing night side could do it. This atmospheric circulation results in one of the wildest weather systems ever found. Imagine winds screaming at thousands of miles per hour, transporting vaporized rock and metal from the day side to the night, where these materials condense and fall as rain in the form of molten minerals. You'd think the gap between the day and night temps would be a whopping 3,000 degrees, yet somehow the atmosphere levels things out with convection. Currents that work in conditions no lab on Earth could mimic. What's truly mind-blowing about this atmosphere is how it even exists in the first place. The hell planet's atmosphere can't be left over from when it was formed due to the solar winds from its nearby star having long since blown away any original gases. So, scientists reckon it's a secondary atmosphere constantly bubbling up from the planet's interior. Imagine a place where the crust is literally boiling. The intense heat and tidal pull from the nearby star are basically cooking the planet from the inside out, causing carbon-heavy stuff deep underground to vaporize and escape through volcanic vents. This atmosphere is continuously being wrecked by stellar radiation and then constantly tops itself up thanks to geological processes operating at temps that would make most known materials vaporize. It's a hellish cycle where the planet's belly feeds its own impossible atmosphere. Rock vapor shoots up from the surface, gets whipped around the planet by winds faster than sound, settles on the dark side, and rains back down as metal and stone. It's like the whole planet's been turned into this massive distillation contraption running on the edge of physics. The way 55 Cancri's atmosphere exists opens up the possibility that planets could have gases in way harsher conditions than scientists ever thought. This could seriously change how we think about which worlds might be able to support life. If atmospheres can hang on in such brutal places, maybe they aren't so quick to disappear around planets we've already dismissed as too inhospitable for any kind of atmosphere. Yet, this crazy atmosphere was just the prelude to what Webb found next. The telescope was about to spot a traveler from another star system that would flip our ideas about time on their head. A comet, older than the Earth, the Sun, and everything we know, is zooming through our solar system from way out there. Comet 3I Atlas might look pretty average at first glance. It's about 7 miles wide, made up of ice and rock, and it's on a path that'll swing it past our sun before it heads back to the vastness between stars. But Webb's detailed analysis showed something wild. This interstellar nomad is around 7 billion years old, making it 3 billion years older than our solar system itself. When astronomers followed the comet's steep path through space, they figured out it came from the Milky Way's thick disk, a part of our galaxy packed with ancient stars formed in the universe's youth. This cosmic traveler has been journeying through interstellar space since before the sun was a twinkle in its stellar nursery. It existed long before Earth, Mars, Jupiter, and all the neighbors in our cosmic block. Webb's near-infrared spectrograph uncovered that the comet's coma, the cloud of gas and dust around its core, is dominated by carbon dioxide instead of the water vapor you'd expect from local comets. This unusual makeup drops hints about the chemical vibes of the star system, where it was born billions of years ago. The comet zips by at over 130,000 miles per hour, fast enough to cross the U.S. in under 2 minutes. Its path is unnaturally flat and straight, unlike anything else in our solar system. This space traveler isn't just following our sun's rules, but is instead obeying the gravitational laws of the entire galaxy, seeing our solar system as just another hurdle to hop over. The truly chilling part about this ancient guest is what it symbolizes. Known as 3I Atlas, it's a reminder from a time when the universe was vastly different. 7 billion years ago, the Milky Way was a wild and violent place. Stars were being born left and right, heavy elements were hard to find, and planet-building chemistry worked under unusual conditions. This comet sprang into existence around a star that bit the dust well before our sun even existed. It weathered the storm of its star's demise, possibly from a supernova explosion that obliterated its original solar system, launching it on a trek through the galaxy. For 3 billion years, it wandered through the cosmic void like a frozen time capsule, holding chemical traces from a bygone era. Seeing it now opens up unsettling questions about how many more ancient travelers might be drifting through our solar system unnoticed. 3I Atlas is only the third verified interstellar object scientists have found. But according to models, dozens or hundreds of these cosmic drifters should be cruising through our neck of the woods at any moment. Each one is like a shard of a wrecked world, a slice of cosmic history that's endured disasters we can barely imagine. These objects are like archaeological finds from star systems alive when the universe was just a youngster, holding secrets about galactic conditions. from times no other objects can tell us about. Yet, 3i Atlas also reminds us of the eventual doom awaiting our solar system. In a few billion years, when our sun starts its death spiral, bits of our home might get flung into the emptiness of space, becoming ancient nomads that will leave future astronomers in distant galaxies scratching their heads long after Earth is gone. The ancient comet's flyby is a sneak peek into cosmic timelines that make our human understanding feel tiny. But Webb's surveys unveiled things even weirder than ancient wanderers from long-gone stars. There are 300 baffling objects lighting up space in the early universe, and astronomers are stumped about what they are. The deep dives by the James Webb telescope have unveiled a new array of cosmic beings that simply don't fit any known mold. These tiny red dots appear like little red specks of light dotted across images of the early universe, but their odd traits have scientists at a loss. Each one shines far brighter than it should when you consider what we know about how galaxies and stars were formed in the universe's early days. The puzzle starts with their color. In the world of astronomy, red light generally signals either incredible distance or cooler temperatures. These things are definitely far out there, around when the universe wasn't even a billion years old, yet they're incredibly bright. They're cranking out a massive amount of energy through mysterious processes, creating a mix of traits that don't fit with any modern universe object. Using cutting-edge techniques like infrared imaging and spectral energy distribution analysis, researchers at the University of Missouri picked out 300 of these puzzling objects from Webb's data. Each looks to be about the size of early galaxies, but shines way more brightly than galaxy-building theories would suggest. If they are galaxies, they're like nothing seen today. They're so luminous they make experts rethink how galaxies might have formed in the universe's dawn. Traditional theories say that the first galaxies grew slowly, gathering matter via gravity over countless years. Yet these little red dots propose that something was whipping up huge, bright structures much quicker than current ideas propose. This is where the riddle gets even deeper. When astronomers try to pinpoint what's generating all this light, the results just don't add up. Some objects appear like tiny points, hinting they might get their energy from supermassive black holes instead of widespread star formation. Others have extended structures, indicating they could be real galaxies experiencing a crazy fast process of star birth. The most unsettling idea is these objects might belong to an entirely unfamiliar stage of cosmic evolution. Back when the universe was in its first billion years, things were way different from now. Matter was thicker, dark matter interactions happened more often, and the cosmic web's large-scale framework was still taking shape. Maybe these unique early conditions allowed the creation of objects that just can't form nowadays. Some tiny red dots show signs of super high-energy processes. They're giving off X-rays, ultraviolet radiation, and infrared light in a way that points to wild, chaotic bursts of energy. Whatever's fueling these objects is working under intense conditions, really pushing the edges of what we know in physics. They seem scattered randomly across space instead of clumped in areas where early galaxy formation was thought to take place. This randomness hints they might be a core characteristic of the early universe, rather than just strange, isolated events. Bang Jing Sun, the grad student heading the research, stresses that even if just a few of these objects are verified to have existed in the early days of the universe, it would compel scientists to rethink current theories on how galaxies form. The sheer quantity of these strange objects Webb has found implies our knowledge of cosmic evolution during the universe's youth is far from complete. These little red dots possibly pose the biggest challenge to cosmology that Webb has uncovered, but their mystery is nothing compared to another. What? The telescope discovered about the universe's large-scale structure itself. Galaxies across vast expanses of space are spinning in sync, hinting the universe might have been born rotating. In what might be one of James Webb's most mind-boggling discoveries, astronomers found hints that galaxies stretched millions of light-years apart are rotating in coordinated ways. This cosmic ballet challenges our grasp of how structures form in the universe. It opens the door to the idea that the entire universe was born with a preferred spin direction. This finding came from Webb's Advanced Deep Extragalactic Survey, where 263 galaxies were observed. As astronomers looked into these distant star systems' orientation and spin patterns, they spotted something that, by standard cosmology, just shouldn't happen. Galaxies that are way too far apart to exert any gravitational pull on each other are spinning in the same directions. Imagine finding that every windmill across a massive region is spinning in precisely the same way, even though there's no wind pattern to orchestrate their movement. These galaxies are set apart by such vast distances that light from one would take millions of years to travel to the other, yet they're part of the same cosmic dance. Leo Shamir, the computer scientist who led the study, pointed out two potential explanations for this phenomenon, and both are quite unsettling. The universe might have started off spinning. If the Big Bang came with its own spin, it might have set a certain rotational direction for everything that formed afterward. This idea fits with a theory that our observable universe could be the inside of a giant black hole in some bigger universe. If that's true, the rotations that Webb noticed could show how the black hole's spin spreads out in ways we don't yet get. Another possibility is even more unsettling for traditional cosmology. If the universe wasn't spinning from the start, these aligned galaxy rotations could mean our current ideas about how the universe evolved are way off. Maybe there's some mysterious force or field at work on scales much bigger than anyone imagined. This would affect more than just how galaxies are formed. A universe that's rotating would be very different from the still universe described in standard models. Space and time might favor certain directions, throwing off the balance in physical laws that could change things from particle physics to the ultimate destiny of the universe. This finding also stirs up questions about dark energy, the force causing cosmic expansion. If there's a preferred spin direction, dark energy's effect could change based on direction, making some parts of the universe expand more quickly than others. This might explain some of the odd findings Webb has about cosmic expansion speeds. Perhaps the most startling idea is that a spinning universe hints at a bigger, unseen structure beyond our view. We could be in just one piece of a mind-bogglingly vast multiverse where whole universes spin around like galaxies in some higher dimensional space. The aligned spins of these galaxies aren't just a twist in how cosmic structures form. They challenge our fundamental grasp of what space is. But these hidden spins of the universe are only the start of the challenges Webb is posing to established physics. Next up, the telescope uncovered black holes forming in ways that defy the rules. There's a supermassive black hole materializing before our eyes through a process that upends everything we thought about star life cycles. In deep space, James Webb witnessed a galactic collision, crafting something never seen before. The Infinity Galaxy, as astronomers call this system, hosts a supermassive black hole forming from direct gravitational collapse instead of coming from dead massive stars. This is happening in a spot where, by all accounts, a black hole shouldn't exist. This black hole finds itself floating amid a great stretch of glowing hydrogen gas between two colliding galactic centers. Normally, in galaxy mergers, supermassive black holes from each galaxy spiral toward one another, forming pairs that either merge or result in one being flung away. But the Infinity Galaxy breaks this mold with a black hole in a kind of gravitational limbo. Peter Van Dockum and Gabriel Bramah spotted this system in Webb's deep field images. The galaxy's unique figure 8 outline caught their eye, but further study revealed something much more significant. Radio signals from the area zeroed in on a massive black hole sitting exactly where it's supposedly impossible. This direct collapse acts like a cosmic landslide. When the two galaxies collided, they unleashed massive streams of gas flowing between their centers. Under just the right conditions, these gas streams became so heavy and compact that they collapsed into a black hole without forming stars first. It's a gravitational collapse, skipping the usual step of star formation. This breakthrough clarifies one of Webb's most mind-boggling discoveries. The telescope spotted gigantic black holes in the early universe that seemed far too massive for their age. Normally, black holes form after big stars live, evolve, and explode in supernovae, a process that takes ages. But Webb found supermassive black holes already around just 600 million years after the Big Bang. Direct collapse black holes grow massive more quickly since they start with so much material. Instead of beginning as small black holes and growing by gathering more material, they start off with huge masses, potentially millions of times bigger than our Sun. This gives them a head start to become the colossal black holes Webb observes in the early universe. The Infinity Galaxy acts as a live lab for exploring this rare formation process. The black hole is actively gobbling up gas flowing between the crashing galactic centers, gaining size while astronomers watch. This system shows black hole formation can be much more dynamic and swift than scientists expected. Yet, the direct collapse model also raises unsettling questions about early cosmic chaos. If this was common in the young universe, it suggests galaxy formation involved catastrophic events creating massive objects in an instant. This process indicates that supermassive black holes might be key to cosmic structure rather than just byproducts of galaxy growth. They could be primary forces in how matter organizes on a grand scale. The Infinity Galaxy's direct collapse black hole shows the universe has ways to make massive objects faster and more violently than traditional models suggest. But even this swift black hole formation didn't account for the extreme behavior Webb would soon find. The telescope's upcoming discovery was a cosmic behemoth consuming matter at rates physics deems impossible. A black hole in the early universe is devouring matter 40 times faster than physics says it should, growing at unimaginably rapid rates. Amid countless X-ray sources in deep space, James Webb found a supermassive black hole defying the basic rules of cosmic feeding. Known as LID 568, this object is consuming matter 40 times faster than its theoretical limit. a rate so extreme it challenges our understanding of black hole physics. Scientists call this maximum consumption rate the Eddington limit. It's like trying to drink from a fire hose. Beyond a certain flow, pressure becomes too strong to allow more intake. Somehow, LID 568 is managing to gulp down from 40 fire hoses at once. This discovery took a mix of Webb's infrared capabilities and data from NASA's Chandra X-ray Observatory. Initially, LID 568 was hidden among countless bright X-ray sources, completely invisible to optical telescopes, but shining bright in high-energy radiation. Thanks to Webb's impressive infrared powers, astronomers could spot the faint emissions that uncovered what this object really was. What's truly unsettling about this black hole's hunger is what it means for its growth rate. With such intense feeding, LID 568 could have put on most of its current mass in just one wild feeding frenzy. Astronomers say the black hole is gobbling up vast amounts of matter in a cosmic blink of an eye. This thing emerged just 1.5 billion years after the Big Bang, back when the universe was barely getting started. For a black hole to reach such a massive size so soon, while still following normal feeding rules, it would have needed to start off with seed masses that are just unthinkably huge. This crazy feeding pace of LID 568 might be the key to solving the puzzle of such cosmic timing. The rapid gush of material flowing away from the black hole suggests its mass growth likely happened in similar wild feeding frenzies. These weren't slow, gradual processes spread over billions of years, but rather bursts of violent consumption that could boost a black hole's mass significantly in mere cosmic moments. The mechanics behind such intense feeding are still not fully grasped. Somehow, the black hole is managing to balance the feeding process despite radiation pressures that should be driving away its food. It might have developed a trick to control the radiation pressure, or maybe the surrounding matter has some property that helps it hold on tight. LID 568 is an extreme case of black hole feeding, really pushing the limits of known physics. This finding suggests that the early universe was home to feeding events far more intense and rapid than what we see today. These quick-fueled ghosts might explain how supermassive black holes got so big so fast in the cosmic timeline. Instead of growing bit by bit over billions of years, they went through short, intense feeding binges that boosted their size massively. But LID 568's unrealistic feeding rate was just one weird thing Webb unearthed in the early universe. The telescope's explorations were indicating that the universe's early days were significantly more chaotic and intense than anyone had guessed. Massive galaxies sit silent and lifeless in areas where they should be bursting with star formation, leaving astronomers scratching their heads as to why they stopped growing. James Webb has spotted what researchers are dubbing sleeping beauty galaxies scattered across the early universe. These huge star systems somehow switched off their star-making activities when they should have been in high gear. These cosmic behemoths contain billions of stars, but don't seem to be making any new ones, going against everything we thought about galaxy development in their early days. This was discovered when astronomers looked into galaxies formed between 600 million and 6 billion years post-Big Bang. In this era, the universe brimmed with gas and dark matter, perfect conditions for swift star birth. Most galaxies from that time should be radiating with light from new stars, rapidly guzzling gas to create new stellar communities. Yet, Webb found many massive galaxies that seem to have slipped into a cosmic nap. These systems, boasting star masses similar to our Milky Way, show none of the lively starbirth one would expect from younger galaxies. Imagine vast cities where construction suddenly ceased and nobody knows why. Called sleeping beauties, these galaxies are stuck in a kind of deep sleep during what should have been their most bustling time. Much like the fairy tale princess who dozed off due to a spell, these galaxies stopped evolving right at their prime. However, unlike the fairy tale, we can't pin down what stilled their cosmic growth. Scientists have floated a few ideas, each challenging core beliefs about how galaxies evolve. One theory posits that supermassive black holes at their centers grew so active that they overheated surrounding gas, halting star formation, an effect known as active galactic nucleus feedback. Yet, the timing seems off. Evidence shows that these sleeping beauty galaxies ended star formation before their black holes could get active enough to heat the entire galaxy. Hence, something else must have kicked off their snooze. Another idea is that these galaxies burned through their gas so quickly in an initial star-making frenzy that they just ran out of fuel. This hints at star formation rates way higher than current models predict, suggesting early galaxies were star factories, unlike any we're familiar with today. The most unsettling possibility is these galaxies hit some unknown process that no longer exists. The early universe had different physical conditions, thicker matter density, and different dark matter layouts, possibly allowing for star-stopping mechanisms we've never witnessed. Dormant galaxies in the early universe turn our ideas about cosmic growth on their heads. If hefty galaxies could stall their growth so soon in cosmic history, it implies galaxy evolution is far trickier and less predictable than we thought. These cosmic sleepers are proof that the early universe was far wilder and more chaotic than our theories suggest. Meanwhile, a rogue planet floating through space shows off the strangest atmosphere with iron and magnesium mineral cloud layers. SIMP 01136 plus 0933 is unlike anything in our solar system. Drifting starless, it glows only with its own faint heat. James Webb's observations unearthed an astounding atmospheric setup. This planet has a layered atmosphere where iron rain pours through magnesium mineral clouds. It's like a galactic desert with different metallic clouds stacked at various heights. Close to the surface, dense iron clouds bring about weather patterns like nothing on Earth. Here, iron condenses into a wild storm, dropping as liquid rain. Further up, another layer of clouds made from forsterite, a magnesium-rich mineral found in meteorites, spins up a whole different weather scenario. These silicate clouds form only when conditions letting magnesium compounds vaporize and condense are just right. When these two cloud layers interact, they create atmospheric dynamics that push the limits of what we understand about planets. Webb's infrared observations showed that both cloud layers are patchy and always changing, hinting at active weather driven by the planet's rotation and internal heat. Interestingly, the iron clouds seem to move differently than the magnesium ones, forming a complicated three-dimensional atmospheric structure that varies greatly across the planet. However, what's most intriguing about this planet's atmosphere lies above both cloud layers, where Webb found what researchers call hotspots. These hotspots are super hot zones powered by radio auroras, electromagnetic phenomena akin to Earth's northern lights, but at energy levels that would be deadly to life as we know it. The presence of radio auroras suggests that SIMP 0136 has an incredibly strong magnetic field, much stronger than anything found in our solar system. This magnetic field interacts with charged particles in space, creating electrical currents that heat parts of the upper atmosphere to temperatures hotter than the metallic cloud layers below. Alison McCarthy, the grad student leading the atmospheric study, noted that the planet shows variability mechanisms that were theorized but never directly seen before. The complex interaction of iron clouds, magnesium clouds, and radio auroras forms an atmospheric system that follows principles new to us. The presence of such complex atmospheric chemistry on a rogue planet raises some unsettling questions about how planets form and evolve. SIMP 0136 has somehow developed and maintained this intricate atmosphere while floating through the cold void of space, far from any star's energy. This could mean rogue planets might support more complex atmospheric processes than scientists thought before. If a single drifting planet can have iron rain and magnesium clouds, there might be millions like it in the galaxy, each with its own unique atmospheric phenomena we've never considered. The metallic rain world introduces a new kind of planetary atmosphere that challenges our understanding of possible weather systems in the universe. A strange galactic formation resembling a cosmic owl is gliding through deep space, exposing tentacle-like structures that suggest violent, unseen interactions. When James Webb captured images of what astronomers nicknamed the cosmic owl, they were initially struck by its unique appearance. The galaxy's bright center looks like two glowing eyes, while the surrounding gas and dust draw the outline of an owl-like face. But a more in-depth analysis showed this cosmic owl to be stranger and more unsettling than its whimsical name implies. It belongs to a category called jellyfish galaxies, which appear to swim through space with long trails of gas and stars behind them. These trails aren't just decorative, but evidence of violent stripping processes tearing the galaxy apart as it moves. The galaxy is experiencing what's known as ram pressure stripping, where moving through the hot gas in galaxy clusters creates a cosmic force that blows away parts of the galaxy's structure. Picture cruising down the highway in a convertible while your loosely packed stuff starts zooming out from the back seat. That's kind of what's happening to this cosmic owl as it zooms through space, shedding parts of itself. The Webb telescope, with its infrared eyes, caught the full extent of this cosmic chaos. The galaxy's arms reach out hundreds of thousands of light years, holding on to billions of stars that have been snatched from their original neighborhoods. These stars are now stranded outside the main galaxy, bit by bit drifting off into the vastness of space. Yet, what's scarier than the galaxy losing its pieces is what this scavenging process tells us about galactic neighborhoods. The force needed to strip away so much shows that the galaxy's zipping through a super dense and hot area, much wilder than the usual open spaces between galaxies. This hints that the cosmic web, that massive network linking galaxies across the universe, is rougher and more chaotic than scientists ever thought. Instead of gliding smoothly through space, galaxies are struggling through environments that could literally pull them apart. This jellyfish galaxy effect even sets the stage for stars to form in these cosmic tentacles. As gas peels away from the galaxy and gets squeezed by pressure, it can spark bursts of new stars way out there, far from the galaxy's core. So, while this cosmic owl is breaking down, it's also sparking new stellar life along the way. Webb's findings showed active spots of star-making scattered throughout these tentacles, shining bright blue with the youthful glow of massive young stars. These star nurseries are floating in isolation, billions of light years from the galaxy that birthed their ingredients. Spotting these jellyfish structures all over Webb's deep field views suggests that galaxy eating and stripping happen way more often than astronomers assumed. The universe might be teeming with cosmic wanderers, stars, and gas clouds ripped from their home galaxies, now drifting through emptiness. This cosmic owl is just one face of the turmoil shaping galaxies across vast stretches. But this kind of galactic drama is nothing compared to the star-level chaos Webb spotted in individual systems. Young stars are forming heavy elements in ways that shouldn't even be possible yet, challenging what we know about how stars evolve. The James Webb telescope has spotted these star systems generating elements like oxygen, carbon, and nitrogen at levels completely unexpected for their ages. These star-making regions are crafting complex elements that, according to all known models, should take billions of years to develop through multiple rounds of star birth and death. It all revolves around metallicity, or the presence of elements heavier than hydrogen and helium. Early in the universe, only these light elements were around in abundance. All the heavier elements like carbon and oxygen had to be created inside massive stars and scattered through space when these stars blew up as supernovas. This process is supposed to take time, long enough for the first stars, called population 3 stars, to be made mainly from hydrogen and helium. When these stars ended their lives, they enriched their surroundings with heavy elements, paving the way for the next generation of stars and the beginnings of more complex chemistry. This ongoing cosmic recycling has been happening over billions of years, gradually boosting the metallic content of star-forming areas. Webb has come across star systems that seem to have missed several stages in this process. Young galaxies, which popped up when the universe was under 1 billion years old, display metallicity levels that would normally require several generations of star births and deaths. They're churning out oxygen, carbon, and nitrogen at rates that don't align with their supposed age. The standout example is the galaxy JDES GSC 13-1, spotted just 330 million years after the Big Bang. Spectroscopic analysis blew the lid off with bright hydrogen emission lines and signs of heavy element production, hinting that the galaxy has already been through considerable stellar evolution, even though it's from the universe's baby years. This unlikely chemistry is forcing scientists to rethink our basic ideas about how stars initially formed. Either the first stars were way bigger and had shorter lifespans than our existing models assume, letting them produce and spread heavy elements much quicker, or some unknown process was enriching the early universe with complex chemistry. The first idea suggests that population 3 stars were cosmic behemoths, maybe hundreds of times more massive than our Sun. These stellar giants would have used up their nuclear fuel in a mere few million years, before blowing up in hypernovas that dispersed heavy elements. Across wide space regions, such enormous stars aren't around in today's universe, but early cosmic conditions might have allowed their formation. The second idea is even more unsettling. If unknown processes were making heavy elements back then, it means we're missing key pieces in our understanding of cosmic chemical evolution. Some process other than stellar nucleosynthesis might have been making complex chemistry when the universe was young, creating pathways we've never recognized. The quick metallicity evolution, Webb noted, also changes how we see planet formation and the chances for early life. If heavy elements showed up way earlier than thought, rocky planets and the necessary chemicals for life might have begun forming much earlier in the universe's timeline. These revelations imply that the early universe had a level of chemical complexity that makes our current models seem overly simplistic. A planet circling our closest stellar neighbor keeps popping up and disappearing in Webb's observations, and astronomers are stumped as to why it exists at all. In what's being dubbed the top discovery by James Webb so far, the telescope found a giant planet orbiting Alpha Centauri A, the nearest star, like our Sun, only to lose sight of it during later observations. This cosmic disappearing act has sparked one of the most puzzling mysteries in the field of exoplanet science. Tentatively named Alpha Centauri AB, the planet initially appeared in Webb's data as a thermal signature matching a Neptune-sized world orbiting within Alpha Centauri A's habitable zone. This discovery alone would have been huge, revealing the closest potentially life-friendly planet to Earth ever found. But when scientists tried to confirm this finding with further observations, the planet was nowhere to be found. Follow-up imaging turned up no sign of that thermal signal that had been so obvious in the original readings. The planet either slipped into a spot where the Webb telescope can't spot it, or it just vanished altogether. Scientists have thrown out a bunch of ideas to explain this cosmic vanishing act, each one rocking our usual ideas about how planetary systems work. One theory suggests the planet's got a super long oval-shaped orbit, keeping it far from its star most of the time, and only showing up when it swings, close enough to give off a detectable heat glow. But that's a bit iffy, because any planet on such a wild orbit around Alpha Centauri A would likely be kicked out due to the gravitational tug-of-war with its neighbor star, Alpha Centauri B. The gravitational waltz between these two stars creates tricky dynamics, making it hard for any planet to stick around in a steady orbit. And then there's another explanation that's even spookier. Maybe the planet's real, but is hidden by a thick dust cloud or a ring of debris that sometimes blocks it from Webb's infrared view. If true, this would mean the Alpha Centauri system is a lot more active and chaotic than we thought, with stuff crashing around and stirring things up, enough to hide planets temporarily. Then there's a third idea that's a real head-scratcher about planet formation. Maybe it's not a planet at all, but something still coming together, clumping bits from a disk of gas and dust, making it show up and disappear from Webb's sensors now and then. This would suggest that planet making is still in full swing in Alpha Centauri, despite the stars being really ancient. But the weirdest thought is that Webb might have caught not a planet at all. That warm signal might be something entirely different, like a dense dust cloud or leftover from a star that never formed, floating in Alpha Centauri's outer zones. This disappearing planet puzzle shows us just how much we still need to learn about planetary systems, even ones practically next door. If something can pop in and out of sight in our neighboring star system, it makes you wonder what else might be hidden in other systems out there. The Alpha Centauri Vanishing Act is a good reminder of space's knack for surprises, making us rethink what we thought we knew about how planets and stars work. It's like discovering ancient magnetic fields out there, crisscrossing like human brain networks and being older than anything else we've come across in the universe. James Webb found traces of magnetic fields stretching across vast cosmic structures, forming connected patterns that weirdly mirror the web of neurons in human brains. These fields seem to be leftovers from the universe's earliest days, when it was still figuring out how to piece itself together in ways we can hardly grasp. This discovery came from Webb's peak at the cosmic web, an enormous grid of filaments and empty spaces that map out matter on an enormous scale. Linking galaxies and clusters, these thin gas and dark matter bridges span hundreds of millions of light years, with Webb spotting that they're laced with incredibly complex magnetic fields. The complexity and organization of these fields are unexpected in the universe's younger years. Webb didn't see simple uniform fields. Instead, it came across intricate networks with nodes and connections, structured like biological neural networks. The resemblance is so uncanny that researchers are turning to the same math used to study brain connectivity to delve into cosmic magnetism. These ancient magnetic fields spark big questions about how the universe has evolved. The standard thinking is that magnetic fields in space develop gradually alongside galaxies and stars, with stellar winds and supernovae boosting them over aeons. But Webb stumbled upon primordial fields that seem to predate this whole process. They even seem to have played a role in early galaxy formation that current theories haven't figured out yet. These magnetic fields, along with events like magnetic reconnections, may have influenced how gas clumped together to form the first stars, impacting their sizes, formation speed, and the chemical makeup of early galaxies. The craziest part is how these magnetic networks hint at deeper aspects of cosmic structure formation. The brain-like patterns suggest that the universe started getting complex way earlier than scientists ever imagined. Instead of just gravitational forces shaping the cosmos, the early universe might have worked like a giant processing system. The network of magnetic fields doesn't just sit still either. Connections form and break over cosmic time. Webb even found that entire galaxy clusters experience magnetic storms, shifting star formation and galaxy evolution across large swaths of space. This shakes up what we know about dark matter and dark energy. Magnetic fields can change how charged particles and matter group together. If these primordial magnets were more powerful and intricate than current models assume, it might clarify some of the puzzles Webb noticed in how cosmic structures form. These brain-like magnetic networks are a game changer for understanding complexity in the universe. If the universe had such organized structures as far back as the time of Webb's primordial past, it suggests there are innate tendencies toward complexity that we've overlooked. These ancient magnetic fields could show that the universe has properties similar to living systems, with unknown information processing and organizational abilities. A massive black hole at our galaxy's core is acting in an erratic rhythm, hinting at unknown physics at play around space-time's edge. Sagittarius A, the colossal black hole at the heart of the Milky Way, has been throwing curveballs at astronomers for ages. Yet, James Webb's observations revealed something unique. The black hole shows off random brightness fluctuations, almost like a chaotic heartbeat. Webb's near-infrared camera zeroed in on Sagittarius A over 48 hours in sessions through the year. What emerged was a black hole constantly changing, with its surrounding accretion disk showing non-stop but chaotic light variations punctuated by sudden, dramatic flares. This showed a region around the black hole's edge bubbling with light changes. Out of nowhere, enormous radiation burst from the disk and then quieted down. These flare-ups seemed entirely random, baffling scientists who can't identify any hidden patterns or rhythms. Farhad Youssefzadeh, a professor at Northwestern University, is at the forefront of this groundbreaking research, describing the behavior as something they've never seen before in supermassive black holes. The team couldn't spot any patterns in the activity, hinting at physical processes that current scientific models don't quite grasp. They suspect two mechanisms are driving this cosmic pulse. Short-lived fluctuations seem to stem from turbulence in the accretion disk, where magnetic fields interact, squeezing plasma and creating brief bursts of radiation. Imagine it as cosmic lightning flashing in the superheated gas, spiraling into the black hole's event horizon. The larger flares, however, suggest something deeper is going on. These huge spikes in brightness could be from massive chunks of matter plunging into the black hole's photon sphere, that eerie zone where light starts. To orbit the black hole before deciding to escape or plunge past the event horizon forever. This unpredictable behavior hints that the Sagittarius A star is livelier than astronomers ever guessed. Far from being the quiet, slow-eating giant from the textbooks, the Milky Way's central black hole seems to be in a constant state of low-key mayhem, gobbling up matter in a series of surprise feasts. What's really unsettling about this behavior are the implications for black hole physics close to the event horizon. The brightness flickers arise from areas distorted by intense gravity, making matter and energy act in ways that stretch the limits of general relativity. The chaos in brightness changes implies that quantum effects could be influencing black hole behavior. Around the event horizon, where classical and quantum physics dance uneasily together, we might witness phenomena that occur nowhere else in the cosmos. The cosmic heartbeat also makes us ponder the fate of information falling into black holes. If the accretion disk behaves truly randomly, it might mean black holes annihilate information in ways that challenge core principles of quantum mechanics. The irregular pulsing of Sagittarius A star offers us a close-up view of physics at its most intense, where gravity's grip is so fierce that space and time start to unravel. Invisible forces mold the universe's very fabric, leaving galaxies ripped apart and scattered across the cosmos. James Webb has uncovered clues that dark matter, the strange stuff making up 85% of all matter, plays a role in these violent cosmic rearrangements. These dark matter catastrophes work through mechanisms hidden except for their wrecking effects on regular matter. Webb's findings come from observing galaxy clusters, cosmic metros, where hundreds of galaxies cling together under massive dark matter's gravitational sway. When these cosmic metropolises collide, they unleash some of the universe's most powerful events, unleashing energy equal to billions of supernovae. But Webb's sharp eye revealed the mayhem reaches far beyond those visible crash zones. Galaxies, millions of light years from these cluster impacts, show signs of violent disruptions by gravitational forces that only dark matter interactions on an unfathomable scale can explain. The telescope picked up on widespread streams of stars and gas, linking galaxies over huge distances, forming bridge-like paths between different galactic systems. These streams are basically what's left of galaxies torn apart by dark matter forces during their interactions in clusters. The unsettling part about this cosmic destruction is how it's hidden from us. Normal matter interactions light up the sky with bright displays, but dark matter collisions don't bring any light, heat, or electromagnetic clues. All we have to go on are the gravitational influences these events have on visible matter. Webb's ability to see in infrared has exposed the full scale of this dark chaos. Faint streams and tidal tails reach out for millions of light years around galaxy clusters, weaving massive webs of disrupted matter that earlier telescopes couldn't catch. Every stream signifies a galaxy that's either partly or fully dismantled by dark matter encounters. This level of destruction suggests dark matter isn't just a passive gravitational structure for the universe. Instead, it's actively reshaping the universe with violent processes that can hurl galaxies from their clusters, strip away their gas, and spread their stars into the space between galaxies. Computer models of dark matter show that these violent events might be crucial to cosmic evolution. Dark matter particles have the potential to collide and interact through gravity in ways that send shock waves through the cosmic web, impacting galaxy formation over vast areas. The most unsettling thought is what this unseen violence tells us about dark matter's true nature. If dark matter is capable of such dynamic interactions, it might possess attributes beyond mere gravitational pull. Some theories suggest dark matter particles could change phases or interact in ways we haven't unraveled yet. Realizing the extent of dark matter's violent role also reshapes our understanding of how galaxies evolve and the way the cosmic structure forms. If galaxies are routinely torn apart and rebuilt through dark matter's influence, the universe could be far more dynamic and chaotic than our models suggest. These hidden disasters are a fundamental part of cosmic growth, working entirely beyond our direct sight and shaping the universe through violence we only recognize long after it occurs. There's a distant galaxy warping space-time so dramatically that it shows up in several spots at once, causing gravitational effects that test our grasp of general relativity. James Webb identified a galaxy with such mass and density that its gravitational pull creates multiple images of itself across the sky, each capturing the same star system at varying stages. This intense gravitational lensing highlights space-time bending at extremes that challenge the limits of Einstein's general relativity. Known as strong gravitational lensing, this happens when an object is massive enough to distort space-time like a giant cosmic lens. Light from objects farther away follows these bent paths, leading to distorted or multiple images appearing unexpectedly in different parts of the sky. But this galaxy takes lensing effects to new heights never seen before. Webb spotted at least 4 separate images of the same distant galaxy, each image enlarged differently and capturing the star system at various moments in time. The gravitational field here is so strong that light takes different times to travel down each curving path. Because of this time delay effect, astronomers watch multiple versions of the same galaxy's history unfold at once. One photo shows the galaxy from 800 million years ago, while another reveals how it looked a billion years earlier. This lensing galaxy works like a cosmic time machine, letting us observe stellar evolution over different periods. The mind-blowing part is what this suggests about the mass within the lensing galaxy. It must hold dark matter much denser than what's predicted by current models. This dark matter clumps in ways that challenge our understanding of how these mysterious particles behave and arrange themselves. The lensing also uncovers dark matter substructures that shouldn't be there according to standard cosmological theories. Instead of smooth halos of dark matter around the galaxy, Webb found evidence of clumps and gaps, hinting at intricate internal dynamics driven by unknown forces. Examining the time delays between different lens images provides solid proof of space-time curvature in line with general relativity. But the extreme lensing drifts into areas where quantum gravity might start messing with classical space-time. Perhaps the creepiest part is what this implies about the abundance of such intense gravitational zones in the universe. If one galaxy can bend space-time this much, there could be many more regions where space and time morph beyond our current understanding or ability to map. Additionally, the various images show that the lensed galaxy is rapidly changing itself, with star birth speeds fluctuating wildly between different time snapshots visible in each picture. This gives rare glimpses into how galaxies develop during their most dynamic periods. The time warp galaxy acts as a natural lab for studying general relativity in extreme scenarios, showing how massive things can literally reshape space and time's framework around them. These gravitational effects kick in on scales where classical physics falters, possibly uncovering new cosmic structures dancing between general relativity and quantum mechanics. All across the universe, stars are engulfing their partners in extreme displays that forge entirely new types of cosmic blasts. The James Webb telescope has caught stellar cannibalism happening all over space, showing binary star systems often end in catastrophic episodes where one star devours the other. These cosmic feasts lead to some of the most intense explosions known, with energies that can eclipse entire galaxies. This all starts when two stars orbit closely enough for their outer layers to meet. The heftier star slowly siphons material from its partner, forming blazing streams of hot gas spiraling into radiant accretion disks. What begins as a slow feed can suddenly escalate into a full-blown consumption event. Webb's infrared capabilities have uncovered these starry feeding frenzies in astonishing detail. The telescope can peek through the layers of gas and dust that usually hide such intense happenings. It reveals how matter flows from one star to its companion, engaging in intricate gravitational movements that culminate in cosmic cannibalism. The most dramatic scenarios involve white dwarfs, the compact remains of deceased stars that, despite their Earth-like size, pack the mass of the Sun. When these cosmic predators leech off their neighboring stars, they can ignite thermonuclear eruptions called type Ia supernovas, which momentarily blaze brighter than billions of regular stars. But Webb has uncovered even more intense stellar cannibalism involving neutron stars and black holes. When these incredibly dense bodies devour their partner stars, they set off kilonova explosions, crafting heavy elements like gold and platinum, and sending out gamma-ray bursts detectable from billions of light years away. The telescope has recorded the entire cycle of stellar cannibalism, from the initial stages where companion stars start losing their material, through rapid accretion phases where the feeding frenzy quickens, to the final explosive events that scatter heavy elements into space. What's perhaps most unsettling is how frequent these cosmic feeding episodes seem to be. Webb studies imply that stellar cannibalism might play a fundamental role in the universe's chemical evolution, creating and spreading many crucial, heavy elements needed for planet and possibly life formation. The intense nature of these events also impacts nearby star-forming regions. These explosions can kickstart or halt star creation over large areas, introducing effects that alter galactic evolution on scales far beyond the original star pairs. Webb has also found signs of incomplete cannibalism events where binary systems start consuming each other but get interrupted before reaching catastrophic outcomes. These cosmic near misses leave behind strange stellar leftovers with unique features not seen in our local galaxy. The frequency of stellar cannibalism is making astronomers rethink how binary star progression influences cosmic chemical evolution. Instead of stars leading solitary lives and fading away peacefully, many engage in fierce feeding interactions, ending in massive explosions. These cosmic banquets are one of the main ways the universe generates and disperses the heavy elements essential for complex chemistry and possibly life itself. Increasing proof hints that reality might unravel on cosmic scales, exposing gaps in space-time structure that challenge our most basic physics. Understanding James Webb's most unsettling finding might not be a single object, but the growing evidence that space-time becomes unstable under the extreme conditions scattered throughout the cosmos. The telescope has detected odd gravitational patterns, unusual energy signals, and structural quirks, suggesting that the smooth space-time fabric outlined by general relativity is more delicate than previously thought. This evidence comes from various sources within Webb's surveys. Gravitational lensing effects around some massive entities don't precisely match general relativity predictions, showing minor but constant deviations. That could hint at space-time structure failing under intense gravitational strain. These oddities appear near black holes in galaxy cluster centers and other massive cosmic structures. Quantum mechanics suggests that at the tiniest scales, space-time should be frothy and chaotic, with virtual particles and energy shifts creating a turbulent quantum froth underlying smooth classic geometry. However, Webb's observations propose that this quantum froth might rise to macroscopic levels under certain extreme conditions. The telescope has picked up strange energy emissions coming from areas where you wouldn't expect to see quantum effects. This includes puzzling radiation from the edges of black holes and weird heating in galaxy cluster centers. It's possible that during intense cosmic events, what's known as quantum foam is spilling into the normal space-time realm. What really catches the eye is Webb's discovery of what's called cosmic strings, hypothetical, super-thin imperfections in space-time that might have come about at the dawn of the universe. If these things are real, they could be seen as fundamental cracks in the universe, spots where space-time is literally torn or bent in ways that break our usual understanding of how things work. The telescope has found a few potential cosmic string signs, including odd gravitational lensing patterns that don't match any known arrangement of matter or energy. These discoveries hint that the universe might have permanent marks from its chaotic beginnings, defects that remain as weak spots in the fabric of space-time. Webb has also uncovered signs of vacuum decay events, indicating regions where the quantum vacuum has shifted to a lower energy state, unleashing huge amounts of energy. These events might represent major changes in the very foundation of reality. The mounting evidence points to a universe that's walking a finer line of stability than we previously thought. Under extreme conditions, like those involving massive gravity fields, high energy densities, or strange states of matter, the basic structure of space-time might wobble. These breaches in the quantum foam carry big implications for our understanding of how the universe evolves and its ultimate end. If space-time can become unstable under naturally occurring cosmic conditions, it makes us wonder whether reality itself is more delicate and transient than we believe. Finding quantum effects at such cosmic scales also suggests that the boundary between quantum mechanics and general relativity might be more flexible than current theories suggest. This discovery has far-reaching effects on our understanding of black holes, space science, and the very essence of reality. The synchronized rotation of galaxies and odd cosmic expansion behaviors hint that we might actually be living inside a black hole, nestled in a greater universe. One of the most spine-chilling ideas suggested by James Webb's findings is that everything we can observe in our universe might be inside a colossal black hole that's part of a larger cosmic framework. This black hole cosmology theory might explain some of Webb's strangest observations, like the synchronized rotations of galaxies and contradictions in how fast the universe is expanding, things that have thrown traditional cosmology for a loop. The clues start with the galaxy rotation patterns Webb saw during its deep dives. Galaxies millions of light years apart are spinning in sync, which should be impossible unless the universe itself has a preferred spin direction. In the black hole cosmos theory, this sync would come from our universe, carrying over the spin of the massive black hole that contains it. This idea proposes that what we call the Big Bang was actually our universe crossing the boundary of a gigantic black hole in a space with more dimensions. From our standpoint inside the black hole, it looks like cosmic expansion. But for the larger universe, we're falling toward the black hole's core in a journey that seems infinite because of the time distortion caused by gravity. This story explains why space is expanding faster, something we usually blame on dark energy. As we plunge further into the parent black hole, the twisting of space-time gets more intense, making it seem like the universe's expansion is speeding up. But in reality, we're moving toward areas with stronger gravitational warping. Webb's findings about ancient black holes that existed before stars even formed align with the black hole cosmology theory. These ancient giants might be smaller black holes that existed in the parent universe before we crossed the event horizon. They appear in our cosmic timeline as primordial entities, coming into existence before regular matter could form stars. The synchronized spinning of galaxies that Webb noticed over vast parts of space makes total sense if our universe inherited its spin from a rotating parent black hole. The galaxies aren't mysteriously in sync. They're all part of the same cosmic spin that was stamped onto space-time when our universe was created. The puzzling differences in expansion rates that have baffled scientists fit perfectly with the black hole cosmology theory. Different ways of measuring might be capturing different angles of our movement through the warped space-time inside the parent black hole, leading to apparent contradictions from seeing the same thing from various views. If black hole cosmology holds true, it means that everything we can observe, from cosmic microwave background radiation to the farthest galaxies, exists within the event horizon of a mind-bogglingly massive black hole. We'd be permanently cut off from the larger universe that encloses us, unable to interact or communicate with anything outside our cosmic cell. This theory also implies that black holes within our universe could host entire universes of their own, forming a layered structure of cosmic realms, where each black hole acts as a gateway to a whole self-contained universe with unique physics, evolution, and possibly life. This idea reshapes our understanding of the universe's meaning and our place in the grand scheme, suggesting that what we know as the universe might be just one bubble in an endless multiverse of black hole universes. What James Webb has uncovered doesn't just push our cosmic knowledge, it redefines our human understanding within a universe that's more bizarre and perilous than we ever imagined. Our previous beliefs about how galaxies form, how black holes develop, and how the universe grows have been overturned by Webb's insights. We thought we knew the rules of space, but instead we've found a universe full of unbelievable objects, intense processes, and phenomena running on unheard-of physics. This isn't the orderly, predictable universe our books teach. It's a chaotic domain where galaxies can appear faster than physics allows. Black holes roam freely, and where the very essence of space-time might fluctuate. We're not residents of a tranquil cosmic haven suited for life, but rather in an unruly expanse where reality itself can unravel in extreme situations. What's perhaps most troubling is what these findings say about our cosmic solitude. If we're indeed inside a black hole universe, as the mounting evidence hints, then we're eternally isolated from any larger reality that contains us. Every signal we send, every adventure we undertake is trapped within our cosmic enclosure. The cosmic havoc Webb has exposed also casts a shadow on our long-term survival. The universe is teeming with drifter black holes, rogue planets sending out mysterious signals, and star-devouring events that can eradicate life in vast space regions. Our cosmic vicinity could be more perilous than we imagined. The fast-paced discoveries have also laid bare how little we actually understand about the cosmos we find ourselves in. Even with centuries of astronomical breakthroughs under our belt, the early findings from the Webb telescope have surprised us by challenging what we thought we knew about the universe's development. If we've misunderstood such basic cosmic processes, what else could we have overlooked? The telescope's insights into the birth of galaxies and ancient black holes indicate that the universe reached complexity much earlier than we ever imagined. This suggests that cosmic evolution might take unexpected routes, possibly leading to intelligence and civilization in times and places we've never dreamed of. But what's amazing about Webb's findings is the promise they hold. The astonishing complexity of space might mean that cosmic evolution is much more varied and intricate than our current models predict. If the universe can create galaxies that seem impossible and black holes without cloaks, who knows what types of life or intelligence it might foster, operating on principles we haven't even begun to uncover. Essentially, Webb has shown us that we're just beginning to understand the universe, one that operates under rules we're only starting to see. Each bewildering discovery by Webb, every supposedly impossible phenomenon, is a chance to broaden our knowledge of what's achievable in a universe that loves to break our expectations. Perhaps most crucially, these discoveries highlight that the universe isn't obliged to be easy for us to understand. Reality works by its own set of principles, which might be completely unfamiliar to human thought. Our continued existence and growth depend on aligning our comprehension with how the cosmos truly functions, not how we wish it would. The strange, chaotic, and often puzzling universe that James Webb has unveiled is the only reality we've got, and making sense of it, no matter how unsettling that understanding might be, is our best bet for steering through the cosmic future that lies ahead.